Okay, so what we're going to talk about today is the different way that substances can be found. Now, we know that there's four states of matter: solid, liquid, gas, and plasma. If you're struggling with those, make sure you're going back to that ed puzzle over the states of matter to get yourself the help that you need for each one of those states and the change of state, the difference from solid to liquid, liquid to gas, gas to plasma, and so on and so on. What we're going to talk about today, though, is where can these substances be found? Like, what are these substances? Well, they can be elements, compounds, and mixtures. And then all those substances can be found as solid, liquids, gases, or plasma. So, for instance, for an element, we have elements on the periodic table. And so on that periodic table, we can find 118 elements. And some of those elements are going to be found as solids, most of the periodic table, so like copper. And then we've got two liquids on the periodic table, which is bromine and mercury. And then we've got a few gases, like the noble gases, like helium and neon and argon and chlorine and fluorine and those guys. So everything can be found in the states of matter. Everything can be a solid, everything can be a liquid, everything can be a gas. But when we say they're found as liquids, what we mean is that's how they're found at normal temperature, room temperature, and normal pressure, which is considered 1 atm. So remember, every substance can be found in different forms of matter, different states of matter. But when we talk about them, we talk about them under normal conditions. So let's take a look here at an element. An element is one type of atom, single, which is also called monatomic. Okay, so mono means one on one. I'm going to try to change that to a different color so it's a little bit easier to see there, hopefully. And diatomic, which means two. So di means two. So if we've got a monatomic atom, that might be something like copper, where you've just got a bunch of little copper particles, a bunch of little copper atoms that are all crammed together. Now, a diatomic is going to be when the two pieces of the atom are bonded to themselves so that they actually fulfill their needs. Now, next chapter, when we talk about atoms and electrons, you'll know what I mean by fulfill their needs. Right now, you're just going to have to trust me on it. So, for instance, oxygen is a diatom, and that means that you find it buddied up or partnered up with itself. So oxygen is what is considered a diatomic element. So elements are what we call pure substances. So a pure substance is where there is only one type of particle. So when we look at a particle diagram for element, you're going to see that there's only one type of particle there. Now, compounds then are also pure substances, but this is when you have two or more, types of atoms or compounds, and they are chemically bonded together. Chemically bonded together. So you're going to be able to tell that because you're going to see these substances attached to each other. So let's do good old water. So here's my little oxygen atom. And then I'm going to come down here and I'm going to hopefully maybe change my color. We're going to make it green. Hydrogen is typically white. But here is your lovely little water molecule. Okay? This is a compound. You can see that you've got two or more substances and you can see that they're bonded together. So elements and compounds are both pure substances. Don't get confused on that. And pure substance just means that every particle in that little sample is exactly the same. Now, mixtures are combinations of elements and or compounds that are physically put together. They're physically put together, meaning that if they're physically put together, they can be physically separated. You can find mixtures as homogeneous or heterogeneous. Now, the prefix homo means same. So homogeneous, it's going to appear the same. If you think about iced tea, Kool-Aid, coffee, when you look at it, it looks all the same. That means the particles are spread out evenly, and so it's going to appear the same. Now, heterogeneous, there's a whole bunch of different ways we can look at heterogeneous, but hetero means different. And so this is going to have particles that are going to block light, scatter light. So things that are cloudy are heterogeneous mixtures. And this is because they are not dispersed evenly. You might have big clumps. You might see layering. So things that I think of, Chex Mix is heterogeneous. You can see all the different parts to it. Also, with heterogeneous mixtures, you can take out the parts that you don't like. It's really pretty simple. If you think about Italian salad dressing, you don't like all the stuff, you just want the vinaigrette behind, you can filter out all the chunks. If you don't like pretzels in your Chex Mix, you can take them out and filter them out. Heterogeneous, they're going to appear different, they're going to look different, and you're going to be able to separate these guys out a little bit easier than a lot of times the homogeneous. Now, one more piece that I want to go over on this slide here is that for compounds, these guys have specific ratios. Specific ratios. Oh, sorry, didn't like my screen. So specific ratios. We'll go right here. It's because I'm clicking off the side of it. So what I mean by that is H2O. Water is H2O. There's always 2 hydrogen for 1 oxygen. That's a specific ratio. H2O2 is not water, it's hydrogen peroxide. So when it comes to compounds, they have to come together in very specific ratios. And also the substances now have new properties. So hydrogen and oxygen, 2 very flammable gases, we put them together, they chemically bond, and voila, we have water, liquid that we drink and not flammable. Mixtures do not have specific ratios. So if you want to throw a whole bunch of pretzels in, you can throw pretzels in. You do not have to be in specific format. Like it doesn't have to be so many. All right, we're going to switch slides. As we're looking at our elements, one type of atom is going to be monatomic, and diatomic, remember, is going to be 2. Di means 2. So we have a certain amount of diatomic atoms that these substances will always exist when they're left alone as diatoms. So if I tell you, here's some oxygen, it's never just, oh, oxygen is going to be a diatom. So there's 7 of them, and they actually make a 7 on the periodic table. And the 7 are bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, and fluorine. Now, if you look at them at the periodic table, you're going to have hydrogen up here in the corner. And then as you go down, you have nitrogen, oxygen, fluorine, then chlorine, then bromine, and then iodine. So on your periodic table, it makes this kind of weird 7. You want to know these diatomic elements. Please write them down. So now what we're going to do is we're going to try your hand at these 2 things together, the states of matter, and if you think this is an element, compound, or mixture. So this particle diagram, what do you think it's representing? Hopefully you had a chance to check this out and see how you're doing. First of all, what state of matter this is a gas. You can see that the particles are spread out far away from each other, not a strong attraction. So that's the state of matter. What substance is this? It is an element because there's only one type of particle. So it is a pure substance. And on top of that, it is a diatomic. So hopefully you did pretty well on that first one. We're going to now try our second one. Our next one, go ahead and take a chance and see what this is. For this one, we know it's a gas again because we can see that there is only a spread between the particles, that they are not strongly attracted. They're not close together. So these guys are spread out, low kinetic or high kinetic energy, sorry, because they're spread out. Now I see one type. So this is a pure substance. So I'm going to put PS for pure substance. It is an element, and it is a monatomic element because there's only one type of each particle. Next one, what do you think? Go ahead. All right, for this one's a little bit tricky. Looks like a gas, got some spread out. You notice that these guys are still close together down here. So this could be considered a liquid or a gas. What I would say is it's probably just at the beginning of vaporization that you are having some of these particles start to break free from each other, because down here there's still a pretty good attraction. So on any test, you would be given, there would be definitely a greater distinction. So we can go ahead and call this a gas just because it is spread out a little bit more than we would like. But it, like I said, it looks like it's probably heading over from being a liquid to a gas, probably at that vaporization point. Now you've got two or more substances. You can tell it's chemically combined. So this is a compound, and compounds are a pure substance because every one of these particles is exactly the same. Now for this one, let's check and see how you're doing. This one's a liquid, okay? We see that we've got a closer attraction between the particles. They'd be able to slide and glide. So, oops, sorry, head back. Like I said, this one's gonna be a liquid. That's no, doesn't look like it, but it is. Now, we have got a mixture. So this is our first mixture. Try to get that to look like an M. And it is a mixture of elements that are monatomic and diatomic. So it is a mixture of elements that are mono and diatomic. Now, to tell if you think this is homogeneous or heterogeneous is a little bit difficult. This one would be homogeneous. Why? Notice that it's evenly distributed throughout. You see one here, it's surrounded by two waters. This one's surrounded by two. This one's surrounded by two. It's surrounded by two. You can see it evenly separated out. If it was a heterogeneous mixture, you would see them all clumped together. All right, so now we are throwing in a new piece here. We're going to throw in if we think that this is a physical change, chemical change, and what is going on. Now, this question tells us that there's a mixture separation, no chemical change. As we get better at these, you will not be given that information. So we take a look at this picture and we notice over here that we have a mixture and it is a liquid. They are close together and we have a liquid. We have a compound and we have a compound. So it is a mixture of compounds. On the other side, we get some water and we get some solid salt. We have a a compound of water as a liquid, and we have a kind of looking liquid, should be solid though, of salt. So now we're looking at chemical physical changes. Let's do one more.
Following students to the main office.
Okay, so we're going to do this last one here. So as I take a look at this, I see that I start on one side with these compounds. So I've got a compound here. And on the other side, I have an element and I have a diatomic element. Okay, hopefully that'll catch up. So I see that I took a compound that was chemically put together and separated it out into individual atoms. So this is a chemical change. This whole structure is representing a chemical change. Okay, last thing. Over here, we can tell that we have a liquid. This one right here is pretty close together, is a solid, and this one over here is a gas. That's supposed to be an S. Don't know why it's looking that way. So all we're doing is putting all the pieces together. We start with our states of matter, we then work into element, compound, and mixture, and then we throw in our chemical, physical changes. Hopefully this helps you as you're going into that KIA practice. Please check with me if you have anything that you need help with.